A spiral galaxy spins slowly against the black, its arms glowing with 100 billion stars. It looks peaceful. It looks like it makes sense. But it shouldn't exist. Not like this. Not spinning this fast. If you calculated the mass of every star, every planet, every cloud of gas in that galaxy, and used it to predict how fast the outer edges should move, the numbers would be wrong. Catastrophically wrong. The outer stars are moving so fast, they should be flung off into the void. Torn apart. Scattered across the cosmos. They aren't. Something invisible is holding them in place. Something with mass. Something with gravity. Something we cannot see, cannot touch, and, until recently, didn't even know existed. Astronomers gave it a name. Not because they understood it. Because they didn't. They called it dark matter. And that was only the beginning of the mystery. To understand how strange this discovery really is, you have to understand what we thought we knew. For most of the 20th century, the universe made sense. Gravity pulled on mass. Mass came from stars, planets, gas, and dust, the things we could point telescopes at and photograph. Add up all of that visible material in a galaxy, and you get a prediction. Stars near the edge should orbit slower than stars near the center. Just like planets in our solar system. Mercury races around the sun. Neptune crawls. In the 1970s, astronomer Vera Rubin decided to actually test that prediction. She measured the rotation speeds of stars across dozens of galaxies. The outer stars weren't slowing down. They were moving at almost the same speed as stars near the core, as if the entire galaxy was spinning like a solid disk, not thinning out into empty space the way it should. There was only one explanation that fit the data. Galaxies contain far more mass than we can see. Vastly more. But where is it hiding? Here's where things get strange. Whatever this missing mass is, it doesn't shine. It doesn't absorb light. It doesn't reflect it, block it, or interact with it in any way we can detect directly. It is, in the truest sense, dark. So how do we know it's real, and not just a mistake in our math? Because gravity leaves fingerprints, even when the source is invisible. One of the clearest fingerprints is something called gravitational lensing. When light from a distant galaxy travels toward Earth, it can pass by a massive object along the way. That mass bends space itself, and the light bends with it, like light passing through a lens. When astronomers map this bending around galaxy clusters, they find far more distortion than the visible matter could ever cause. The invisible mass is lensing light on a scale that dwarfs the stars themselves. There's a second clue, even older than starlight. It comes from the very beginning of the universe, the cosmic microwave background, the faint afterglow of the Big Bang, still detectable in every direction we look. Buried in the subtle patterns of that ancient light is a signature, a ratio. And that ratio tells us, with remarkable precision, how much of the universe is made of ordinary atoms, and how much is made of something else entirely. The answer is almost hard to accept. Roughly 27% of everything in the universe is dark matter. Ordinary matter, every star, every planet, every person who has ever lived, makes up less than 5%. We are the minority. But dark matter wasn't the last surprise. In the late 1990s, two independent teams of astronomers set out to measure something that seemed almost routine, the rate at which the universe is expanding. Since the Big Bang, space has been stretching. That much was already known. The question was simple. Is that stretching slowing down, the way you'd expect from gravity pulling everything back together? To measure it, they studied a specific type of exploding star called a Type Ia supernova. These stellar explosions are famous for something remarkable. They all release almost exactly the same amount of energy. That makes them cosmic mile markers, objects whose true brightness we already know, so we can calculate their distance based on how dim they appear from Earth. Astronomers expected to find the expansion slowing down. They found the opposite. The universe wasn't just expanding. It was expanding faster and faster, the farther back in time, and the farther out in space they looked. Something was pushing space apart. not pulling, pushing. And whatever that something was, it had to be powerful enough to overcome the combined gravity of every galaxy, every star, and all the dark matter holding them together. Scientists gave this force a name too: dark energy. And when they calculated how much of it would be required to explain what they were seeing, the number was staggering. Here's the discovery that changes how you see the night sky forever. When you add it all together, dark energy, dark matter, and ordinary matter, the universe breaks down like this. Dark energy, roughly 68%. Dark matter, roughly 27%. Everything else, stars, planets, galaxies, less than 5%. Everything humanity has ever seen through a telescope, every photograph from the Hubble Space Telescope, every breathtaking image from the James Webb Space Telescope, all of it comes from that final sliver. A rounding error in the composition of reality. The rest is shadow. And it isn't a passive shadow. It's active. Dark matter's gravity built the scaffolding that let galaxies form in the first place. Without it, matter would have been spread too thin and too evenly for stars to ever clump together. Dark energy, meanwhile, is quietly winning a cosmic tug-of-war, stretching the fabric of space a little further every single second, in every direction, everywhere at once. The galaxy you were looking at in the opening moments of this video isn't really shaped by starlight. It's shaped by something we cannot see, pushed and pulled by a force we cannot touch, floating inside an expanding void we cannot fully explain. We didn't just discover new objects in the universe. We discovered that we've been looking at the wrong 5% all along. Now, here's what needs to be said clearly. Dark matter and dark energy are not guesses. Their effects are measured, repeated, and confirmed across independent methods. Rotation curves, gravitational lensing, the cosmic microwave background, and the large-scale structure of the universe all point to the same conclusion. But what they actually are remains one of the biggest open questions in science. Dark matter might be made of a particle we haven't detected yet, something that interacts through gravity but almost nothing else. Experiments deep underground, shielded from cosmic radiation, have spent years hunting for a direct collision between one of these particles and ordinary matter. So far, none has been confirmed. Dark energy is even more mysterious. The simplest explanation treats it as a property of space itself, a constant energy built into the vacuum, first proposed in a different context by Albert Einstein. But that explanation creates a new problem. When physicists try to calculate the expected strength of that vacuum energy from particle physics, the prediction is wrong by an almost incomprehensible margin. Some researchers wonder if dark energy is truly constant, or if it changes over cosmic time. Others ask whether our understanding of gravity itself is incomplete on the largest scales. These aren't settled answers. They're active investigations, playing out right now in observatories and particle detectors around the world. The honest truth is this: we've measured the shadow with extraordinary precision. We still don't know what's casting it. Think about that. The next time you look up at a clear night sky, every star you can see, every planet, every galaxy captured by our most powerful telescopes, it's a thin, glowing surface stretched over something far larger and far stranger. We are not standing at the center of the universe. We are barely standing in it at all. 95% of everything that exists is still, quite literally, in the dark. And somewhere out there, in the space between the galaxies, that darkness is still writing the rules of everything we see. Subscribe our channel The Deep Space File for more video, because the space is full of mystery.